Welcome to AI Machine Learning Workshop, the tutorial before your tutorial, part 5, and this is presented by Blackmagic AI. So if you want to find out more about us, go to blackmagicai.com, sign up on our email list, you can like us on Facebook, or subscribe to this YouTube channel. Remember, this tutorial series is divided into two main sections, Part A and Part B. In Part A, we cover the theory and concepts in AI and machine learning. And then in Part B, we apply the theory, concepts, and tools from Part A to actual coding example projects. So in this video, we'll begin our introduction to neural networks, which is the backbone of machine learning. So before we go into more detail in this video, let's recap what we did in Part 4. So in Part 4, we did an introduction to Google Colaboratory. So remember, we introduced Google Colaboratory as a tool we will be using to implement our machine learning solutions and example project. We explained how Google Colaboratory divides our workflow into cells that can be used to document our work and interactively run shell commands and Python code. We introduced the basics of Google Colaboratory user interface to open a new notebook, create cells, view the notebook file system, and change the runtime to GPU or TPU. We demonstrated how to run command line shell commands and Python code interactively. So what is this video all about? Well, this video is an introduction to neural networks. What is a neural network? Well, a neural network is a computer simulation of how the animal brain works, and it's inspired by biology. The key ability is that it can learn to approximate any arbitrary function. All right, so take a deep breath, let that sink in for a minute while I repeat that. Its key ability of a neural network is that it can learn to approximate any arbitrary function. So what does that mean? Think of a neural network as a generic black box Swiss Army knife that can learn to do anything with data and training. For example, your brain contains a neural network capable of reading sheet music as input and translating that into output to make your muscles play music on a musical instrument. And that same neural network can also perform mathematical calculations. Think of these example tasks as functions that describe the relationship between inputs and outputs. And also consider how the same neural network can do these things and many more functions through training, such as laundry. If you look at the diagram on the right here, this is a high-level schematic of a neural network. Each circle represents a neuron, but in our computer simulation of a neural network, we're going to call these perceptrons. All right, so on the left-hand side, we see a column of these perceptrons, or neurons, and that's the input layer. And then if we look all the way on the right side, we see another column, and these will be called the output layer. Now, everything in between, we will call that a hidden layer. Neurons in the hidden layer detect features, and these lines represent the weight between the connections of the different perceptrons. The weights between the neurons in this network, they represent the features hidden in the input patterns. We will go into more detail about neural networks in the series, but in this graphic, this screen will introduce the different types of neural networks. Now, if you remember our discussion about the different approaches to machine learning with neural networks, we mentioned the different ways that neural networks can learn. So as a recap of the difference, we have supervised learning, which is we have a labeled data set. And then we also have unsupervised learning, which is an unlabeled data set. And then we have reinforcement learning, where the neural network learns by maximizing some reward. In this tutorial, we'll be focused on supervised learning, in which we will label our data sets. Now, how do we train a neural network? Well, some key neural network terms that you'll need to know and that we'll cover in more details later in this series are backpropagation. So think of backpropagation as the way we're going to train our neural network. It's a technique we will use to train our neural network. So some of the terms involved in backpropagation are hyperparameters, loss, mean squared error overfitting, and its remedies like data split, regularization, and dropout, etc. So think of backpropagation as the algorithm that applies gradient descent to train a neural network. That's our next term, gradient descent. Gradient descent is a solution to optimization problems. We will try and optimize the mean squared error in our neural network, and we'll use gradient descent to help us with that. We'll talk about the different types of loss and error functions. And this graphic on the right shows just a sample of the many different types of neural networks. So in this tutorial series, we'll be focused on the feed-forward network and support vector machine. So that's this one. But you can see from this graphic, there are many types of neural network architectures, and each one is designed to solve a particular type of problem. As we mentioned in this tutorial series, we'll be focusing on classification type problems and regression type problems, and that's best served by these feed-forward and support vector machine neural networks. You can see there are many more that can be applied to solving specific types of problems. We mentioned also previously that our neural network is composed of something called perceptrons. Recall in part 1 intro how this is an overview workshop, and we'll sacrifice and skip many details in preference for a better understanding of the whole picture of the subject. We'll use a little math in our explanations, but we're going to try to avoid high level like postgrad MIT calculus math for this. So if you have just basic algebra background, that'll be sufficient. The rest will kind of do a lot of hand waving. So in our diagram, we showed those little circles were perceptron. A single perceptron is good for linear binary classification. So this means linearly separable problems. Nonlinear classification requires a multi-layer network of perceptrons with nonlinear activation function. We'll explain more in detail what that means later. If you look at this diagram on the right, this shows a graphical representation of how a perceptron works. All right, so you'll see here, this is our input layer that we talked about before, and we're going to label each input with an X and a subscript. So the first one will be X subscript 1, X n minus 1, all the way to X subscript n. So we can have many inputs, and we'll represent them with this type of notation. Then we'll apply some weight to our input. Now these weights are represented by the W symbol, and the subscript on the weights indicate the input that they apply to. So for example, W sub 1 applies to input X sub 1, and all the way up to W sub n applies to the nth input. So these weights, their purpose is to amplify or dampen the inputs, depending on the input features that they're trying to represent. Then we move on to the next component, which is represented here by the sigma symbol, which means summation. So we're going to take all the weights that are applied to their inputs all the way to X sub n, and then we will sum them together or add them together. And then we'll apply this other component at the top, this constant times a weight, to the entire summation, and then we'll take that output and we'll pass it through a activation function. In this case, we're showing a step function, and then that's where we'll get our output. So we go all the way from inputs to outputs, and this is a single perceptron. So in this graphic, we're going to go into a little more detail of perceptron anatomy and perceptron magic. There's another graphical representation of our perceptron, which remember, this represents a single circle or neuron in our neural network. So a perceptron is the basic building block of our neural network. So right now we're focusing on this single perceptron and its anatomy, and to learn how it works in order to understand the more complex neural network. All right, so let's start again. We have our inputs, weights, we have something called a bias, we have our summation, we have an activation function, and the output. Now these components represent the anatomy of the perceptron, starting all the way from the inputs to the outputs. Once again, our inputs are labeled with an X and a subscript. A subscript is representing the number of that input. So if we have 3 inputs, we will have 3 subscripts ranging from 1 all the way to 3. But we're not limited to just 3, so that's why we say we can have inputs all the way up to X sub n. Component are the weights. So what the weights do, remember, they amplify or dampen the inputs. So we take the weight and multiply it by its corresponding input, the same subscript. So in this case, X sub 1 multiplied by W sub 1, and then that goes into our summation component. And then we do that for all the remaining inputs, and we feed all the way up to x sub n and w sub n, and then we feed those into our summation component. So remember, our summation component is going to sum all these weights multiplied by their inputs. Then we're going to subtract a bias. We will explain more about the bias later, but think of it as a constant that we will subtract from our summation. So once we sum all these inputs multiplied by their weights, we're going to apply this subtraction of a constant to that total summation. And once we get that, we're going to feed it into the activation function. So the activation function, and the activation is applied to our previous component to help customize the output. For example, we might want our output to be binary. We might want to limit the range. We might want it to be positive, negative values, etc. In this example, we're showing a graphic representation of our activation function. And once it leaves the activation function, that's our output, represented by the letter Y. We can get an output or outputs depending on the type of problem we're trying to solve, as you saw in our previous neural network diagram, which showed the input and an output layer with multiple outputs. Now that we have a basic understanding of perceptron anatomy, let's look at this table on the right to see how we can represent that mathematically so that we can simulate it with a computer. All right, so this first column is the mathematical representation of the perceptron diagram. Beginning of our perceptron, we take the inputs and we multiply it times its corresponding weight for that input, and then we sum that together and then we apply our bias. So if you look at this simple notation here, this is the summation notation. So what this means is take x sub I, multiply it times the weight sub I, you sum those together in this part, and then once you get that sum, you subtract theta, or if you want to use the lowercase b representation, it's the same thing. So you may see both of these in references or documentation, but they're the same thing. You can see in this summation notation, each component has a subscript I. So I will range from 1 all the way up to n, depending on how many of these inputs you have and how many weights you have. So just think of that as take my x sub 1 times my w sub 1, add that to x sub 2 to w sub 2, continue that summation until I gets to the last number of inputs that you have, and then we will subtract our bias. On the expanded in 2D column, this represents what if we assume we have 2 inputs. We could have more, so it could be multidimensional, but in this example, we're just going to use 2 dimensions. So we're going to have a subscript index of 1 and 2. So if we expand this equation out in 2 dimensions, this is what it looks like. So we get x sub 1 times w sub 1 plus x sub 2 times w sub 2 equals theta. Now, if we move theta to the left-hand side, then we have our summation minus theta equals 0. Or if you want to use the lowercase b notation, this is what it looks like, but they are equivalent. Now, upon closer examination of this expanded in 2D format, mathematical representation of a perceptron into this expanded 2D format, you will notice that it resembles this equation in the second row. Now, what is this equation? Well, if you look at the equations above, you will see that we still have our x with our subscripts, 1 and 2, for 2 dimensions in this case, but it could be all the way up to x sub n. And then we have a and b, which represent our weights, or w's here, and then we have equal to some constant, so that's also represented here. Now, what is this equation? Well, it's the equation of a line in standard form. So if you look that up, that's what a standard form equation of a line looks like. Now, this equality sign means this is true of any point on the line. So any point on this line satisfies this equation. Now, for all points not on the line, we can say this, that the summation of our inputs times the weights minus theta, it's either going to be greater than 0 or it's going to be less than 0. So if any of the values in this equation satisfy this condition, that means they are not on the line. So either it's positive or negative. And this is how we would determine if a point is on our line. We'll explain why that's important later. Just for now, remember that if we expand the mathematical representation of a perceptron, we get an equation of a line in standard form. Any point not satisfying this equation of our line is not on our line, and when that's indicated by it either being greater than or less than 0, or positive or negative. So that's how we determine if something is on the line of a perceptron. Now we'll explain later why that's significant. So just for now, remember that this is the equation that indicates whether points are on or off of a line that our perceptron represents. That concludes part 5 of AI Machine Learning Workshop, the tutorial before your tutorial with an introduction to neural networks. Go to blackmagicai.com, like us on Facebook, sign up on our mailing list. You can also subscribe to our YouTube channel, and you'll be notified when additional videos in this series are posted. Thank you for watching.